Thank you very much. It's a pleasure to be here today to talk about my passion, which is using math to tackle our unsolved problems of climate change. I would love a clicker. Okay. So at its very basic level, climate change is a chemistry problem. The sun's rays hit molecules in the atmosphere and they trap heat. And those rays could come from the sun or from the Earth's surface. That's the greenhouse effect. And thank goodness we have it. Without it, the Earth's surface on average would be about negative 20 degrees Celsius. But the details matter. So if let me pause that a second. If we have more molecules that release heat or trap heat, the atmosphere warms because there's more of those molecules, and that's global warming. But as I mentioned, the details are the ball game, and that's where physics comes in. Oh, sorry, guys. The physics isn't showing, but that's okay. So, imagine a world with physics. So you have the sun's rays that come in, and they come in unevenly. That's why we have the poles and equator, right? And the Earth has a rotational tilt to its axis. So as it travels around the sun, we have seasons. So local climate is variable, right? And the big one, there it goes, excellent. So the ocean, the land, and the ice all absorb and release heat differently. That's why we each have our own local climate. It's why some of us have a lot of rain and some of us don't, and different types of weather patterns and all those things. And physics helps us understand that. Now, let's not forget biology. We just heard about that. Biology is critically important, too. It helps regulate and it helps support our greenhouse. The plants, the soils, and the animals all contribute to releasing and absorbing air that impacts their climate as well. But the great connecting part of this is math. Here, applied math. It is the great explainer, the language that we use to express the science that we're doing. Now, excellent. Okay, so I'm not here to talk about global warming, other than what I just told you. There are many great talks and resources for that, and I'll show some at the end, so if you want to know more. But it's important to think about not the problem, but the solution. And math is helping us with that solution. For example, well, I should start with this. Weather and climate scientists use similar math. They live in the same Earth system, and they're studying the same Earth system. So weather and climate are very linked. But whereas weather scientists look at storms and storm systems, like this beautiful thunderstorm that sat over my backyard last July, they look at that, and then you've got climate scientists who look at patterns and trends. So they take the weather and they look at the statistics of weather. So that's the whole statistics of climate and weather. For example, this storm system, you get different kinds of storms in different kinds of climates. El Nino and La Nina, which we all know is that heat over the equatorial Pacific. It changes year by year. It turns out that that actually impacts storms over places like California and the West Coast US and Central America, and sometimes even closer towards my neck of the woods. We would never have known that had we not had the math and the statistics to understand those remote connections between weather and climate. Let me tell you a story. History is always a fun part of science. So before we knew very much anything about weather and climate, a renaissance of sorts was unfolding in the second half of the 19th century. And a lot of this was happening over Europe. But I'm going to tell you a US piece of the story because it was our storms that generated a lot of the interest. So there was a guy in 1821. His name was William Redfield. He was a New York businessman, but also sort of an amateur engineer. He noticed, he was in Connecticut, that the storm damage was in the southeast direction from a hurricane that had just come up the coast of the US. And he had been in Massachusetts the day before. And the storm damage was going in the northwest direction. That's the orange state you see there. So he was intrigued by that, and he said, well, I'm going to gather data from all over, all the newspaper reports, everything he could get about that hurricane, gathered all the data, and from that decided, I think these storms are great moving whirlwinds. So life went on, and he lived his life, and we all lived our lives. He was on a ship 10 years later, and he saw a math and physics professor from Yale named Denison Olmsted. He tells him about his theory. And Olmsted says, you should publish this. You early career scientists in the audience, you should publish it. It might be actually a good idea. So he publishes his theory. Meanwhile, there's a guy named George Espy. He's a mathematician from Pennsylvania. He sees this, and I should mention, he's interested in cloud physics. So we didn't understand about clouds. Back then, weather scientists didn't understand that water, which is denser than air, could actually rise into the atmosphere as floating clouds. How could it be? So they were working on this problem, and Espy had this idea that actually water vapor would rise in the air and be carried aloft and condense as clouds through these rising air masses called thermals. And any of you who've been on an airplane know what thermals are, right? You go through a bumpy, a cloudy sky, thermals. So he had this theory, but he saw Redfield's paper and he said, that doesn't jive with my theory about cloud physics. So he picked a fight with him. Now, in science and math, picking a fight means you write a strongly worded journal article saying my theory's right and yours is wrong. But he did that, and Redfield saw his paper, Espy's paper, and wrote his own strongly worded article back. So he threw another punch, right? And they bantered back and forth. And this was great because they lit up huge interest in the weather and science community, and the field advanced. So some of Espy's theory was correct, some of Redfield's was correct, and they all got together. And those crazy characters, plus all these other folks who got involved, put together these large equations that we now use to study the atmosphere and ocean. It can't be a math talk without a big set of equations, so you're welcome. Now, don't worry about this. All this is, the Greek letters, the symbols, and all that, this is just all those relationships I was talking about. Just all the different forces that balance, all those things. It's just that mass can't change. You can't create or destroy mass. You can't create or destroy energy. It's all those things in those complicated looking equations. That's how we sound important. So what do we do with them? We solve them. Sure, no problem. Turns out you can't solve them exactly. You have to figure it out the hard way, which is what mathematicians call guessing. They estimate the solution in the future. They plug in the numbers and see how close they are and go, okay, we need to update that solution. And you iterate, you guess even better and better, and you estimate. It's just optimal guessing until we get to a solution. Now the problem is, it's not just one point in the atmosphere that we need that answer. We need to know what's going on in the atmosphere and the ocean and land and ice sheets. We need to know it everywhere, all around the globe, from the ground all the way up to space. We need to know it for all time. So, all is not lost. We take Earth and we make it a grid. What do we do, and how do we do that? Well, there's many ways to make a grid, right? But now we're solving a finite number of problems rather than an infinite one. So we're already infinitely better than we were before. So how many points do we need? Well, if you imagine we want to see a hurricane or model that, we need a lot of points in a very small area near the hurricane, right? So you can see what's going on and resolve it. But if you want to know what the global temperatures will be in 50 years, you don't need as many points. You need to get the general gist of what's happening, but you need it for a long period of time. So we can play with our grids and use it to solve the kind of problem we want to solve. Same thing when you go vertical from the surface out. We can add levels or subtract them based on what we want to see. In fact, this grid here is one that we use a lot. We like this because it's called a cubed sphere. Classic math thing. You take a really complicated problem, you make it a cube, you solve it, you're done, right? But it turns out we have steps, right? You take a simple problem and then you solve the more complicated one from there. If you imagine this as a square balloon, you blow into it and you interpolate out and you get the Earth. So we have tricks and tools to get from the simple problem to the complicated one. So, great. Take out your calculator. Let's start solving climate problems. Well, let's see. OK, so if we want to look our modern problems today, we want to understand both hurricanes and global temperatures. We want to solve them together. So we take about 500 points along a cube face times another 500 points along a cube face. There are 6 cube faces. We want to solve about 100 levels in the atmosphere. We want to know this for about 50 different types of variables. So we want to understand the solution in terms of wind, temperature, cloud physics, meaning, so you want to know all the rain you can have, snow, graupel, sleet, all the stuff we had yesterday. And you want to solve for that. So that's about 7.5 billion points that we need to solve in these equations. Sounds like a lot. Well, Espy and Redfield didn't have this. This is Frontier, and by the way, thank you for that introduction. Oak Ridge has the largest computer in the world according to the top 500 list. Not forever, but for now. And this can solve 10 to the 18 flops per second. Well, I just told you we only needed 10 to the 9 points to solve the problem, so we're good, right? Well, it's a little more complicated than that because we need to know for many time steps, so we have to go forward in time and make our guesses and our estimates. And if you're looking at 50 years and you move forward about 30 minutes at a time, you're looking at another 10 to the 5th problems. And remember, I told you, you don't get the answer right away. You have to estimate and update your estimates. So each time we have to do that. So when you add all those numbers up, you're about 10 to the 15 that you need to solve a full climate simulation. So you really do need one of these computers to solve climate. And of course, we do many of those simulations because we have a lot of problems to solve. So we're very happy to have this computer and take it out for a test drive. It's brand spanking new. We haven't really taken off the plastic yet. What do we get when we're done with all that? OK, I hope this works. Let's try it. Yes. So I'm now showing you an ocean simulation. The ocean models do look so pretty. So we ran a global ocean simulation recently using our climate model. And you can see here, you get to see all the eddies. When you have lots of points to resolve your problem, all the details in the circulation, it's just on a continuous loop. And I've zoomed in here on the North Atlantic because, obviously, you guys care about the North Atlantic. Why? The Gulf Stream, right? So what you have here is hot, salty water in the tropics, and that water moves upward as the Gulf Stream. So those white lines you see are called streamlines, and it shows you the flow on the surface over time. That's the time average flow. And what it does is it takes all that heat, runs up the East Coast, and heads out over towards Europe, where you get much nicer, warmer weather than you would have otherwise. So yay, Gulf Stream. And this black lines here are also streamlines. What happens is that water releases its heat, gets dense, sinks, and then comes back down to the tropics. So it's what we call the Atlantic meridional overturning circulation. Critically important for a lot of the climate and weather that we see in this part of the world. Climate scientists are very interested in this because as the ice sheets melt, they're going to release cold water. And that changes the density of the water that's already there, and it might mess with the circulation. Now, again, I'm not here to talk about the problem, but once we have this tool, using math, we can use it to solve the problem. Once we know what's happening, we can prevent it, we can mitigate it. Once we can see what's happening, then we can start moving forward. And that's the key to math, is finding solutions. I just wanted to mention, I said a lot of different kinds of math in this talk. I talked about statistics, optimization, machine learning, algorithms, all these different things were touched on. That's all different kinds of math, all used to solve these problems. And I'm just going to put this up here in case you want to screenshot it, but these are some resources if you want to learn more about it. Thank you so much.
So you mentioned sort of the scale. How much more would you need? You have like 10 to the 18th flops. it's difficult to wrap your head around how much you would need to say something about the circulation, for instance.
Sure. So the problem I laid out for you, the 10 to the 15, is looking at the scale of large-scale weather and climate. What we really want to know in the future is very localized things. So severe weather could impact, who's talking next? The electrical grid, among those other things. Things like that. We want to understand what's happening on a very local scale while still running very global simulations. So all those points I mentioned, you need to double the amount of points, quadruple the amount of points I just showed on the grid, which doubles and triples your computing power. And actually, it's even more than that because you need more estimates to get to your solution. So it multiplies and multiplies the more finer resolution and things that you want.
And what kind of questions would you optimally want to answer? How small is the scale?
I want to know if it's going to rain in 50 years on Tuesday, the 3rd. When we have more detail, we can make more connections between remote locations, very small things, all the way down to the molecular level, right? There's tons of molecules in the atmosphere. We're not resolving those. We're not resolving individual clouds. There's lots of things that we want to see that we can't see yet.
So more computational time.
Absolutely. I'm hungry for it.
Absolutely. Okay. Thank you so much.
Thank you so much.